So in this part, we're going to focus on a few different things involving the way that circuits work. And you did some stuff with circuits last year. One of the first pieces is we're going to talk about Kirchhoff's laws. And Kirchhoff's laws specifically state the relationship within the circuits. And it's stuff that you've used before and have done before, except this gets into the technical definitions of it. The first law is the conservation of charge, and it says that the sum of the currents into a junction is equal to the sum of the currents away from a junction. And it looks like what we have here. Now, we use this mostly when we're talking about parallel components of a circuit, where you have your main line that comes into the parallel component and it has a specific current. And then that current splits along the paths of the parallel component, and then it comes back together after it goes through the parallel component to be a part of the rest of the circuit again. And so that's how we see it a lot of times. But if you look at the picture that's here, it's not even specifically a single line or, getting into a parallel component. But anytime you have wires that are coming together, whatever the sum is heading into that junction will be the sum of the current heading away, regardless of how it's structured. Kirchhoff's second law is looking at the conservation of energy. And so saying in a complete loop, the sum of the EMFs in the loop is equal to the potential differences in the loop. Remember that your EMF is what's providing the voltage, and then your resistors are using the voltage, the PD that happens with that. And so we use this when we're calculating in a series circuit for what your voltage drop is across each resistor there. And by the time it gets back to the battery, you've used up all of the voltage. And so if you were to add in more batteries and more resistors, it still would be kind of in a larger scale that the sum of everything that's being provided from the batteries, your EMFs, equals all the potential differences. Everything will be used up in that circuit. When we're talking about a circuit that's in series, it looks something like this. And note that the resistors are shown by a box here, which is a little bit different than what you sometimes see. The IB uses a box for the resistors, and a lot of other texts, or another acceptable way of doing it, is by using that jagged line for your resistor. So know both of them, be familiar with both of them. And there are three main things to keep in mind when you're talking about a series circuit. The current through each resistor is the same, so it remains consistent throughout the series circuit. Your total PD on the resistors, like we just talked about with Kirchhoff's laws, when you add them up, they equal your voltage from the EMF. And then the combined resistance in the circuit is the sum of your separate resistors. So remember, when you're in series, you just add up your resistors to get your total resistance. When you're looking at resistors in parallel, they set up something like this. The path for the current splits and heads through each resistor independently, or that path independently, and it's structured something like we have here. Three things to keep in mind when you have a parallel circuit. The potential difference across each resistor in parallel is the same, so each path that you take has the same voltage drop from when it starts to when it finishes. The current in the main circuit is the sum of the currents for each of the parallel branches. And so that splits into however many paths it has, but then it comes back together and they remain equal to each other. And then when you're calculating your R, you have 1 over R for equivalent resistance is equal to 1 over R1, 1 over R2, 1 over R3, adding those together, and then solving for the equivalent resistance. Another thing to keep in mind when you're dealing with parallel circuits is that the equivalent resistance of that parallel component is always going to be smaller than the smallest resistor in that parallel component. So if your smallest resistor is 5 ohms, the equivalent resistance will be less than that. It will always be lower than the smallest one that's there. So if we look back at the schematic that we had earlier, you have 3 paths that the current will go on, and those 3 currents, when you add them up, will equal the total current of the main circuit. And then whatever voltage drop you have across there will be the same for each one. So let's say it's connected to a 9-volt battery. There's no other place that resistance would be used up. And so you would have 9 volts across each resistor that's there. When it comes to the circuit diagrams, as I briefly mentioned before, you'll need to be able to recognize and use the accepted circuit symbols in the physics data book. The IB will always use those and set those up relying on those symbols. So if you're ever not sure what something means, you can look it up there. They will follow whether you draw a resistor as a box or whether you draw a resistor as a jagged line. They can follow either one of those. But just make sure that you're fluid in being able to use and recognize either one of those conventions for that. We've talked a little bit about ammeters and voltmeters. Ammeters measure the current in a circuit, and voltmeters measure the voltage drop across a certain component. And the concept of the way that they work is something that we'll look at, and really the IB also loves to take a look at. So when we're talking about a current, the ammeter will measure the current, and so it has to be in series in the circuit. Now, if it has a big resistance and you put it in series, it's going to affect the overall function of the circuit, and you don't want that to happen. So an ideal ammeter needs to have as little resistance as possible. In a perfect world, it would have zero resistance. Reality is it will always have a tiny bit of resistance. But the smaller it is, the less it would impact the rest of the circuit. What you don't want to have happen is that you put in your ammeter to measure the current, and the current drops because you have too much resistance in there. So when you're talking about an ammeter, the thing to remember is that it will always be put in series with the rest of the circuit in order to figure out the current there. And because it's in series and you don't want it to mess up with the rest of the circuit, you want it to have a resistance of zero. Reality is it won't ever be zero, but as close to zero as possible. So when they talk about an ideal ammeter, it would have a resistance of zero. When we talk about a voltmeter, the voltmeter needs to measure the voltage across a specific component. And we know that when items are in parallel together, each path has the same voltage drop across it. So if you take a voltmeter and put it in parallel with another component, the voltage drop on the voltmeter is the same as the voltage drop on the component. And that's how that's measured. Now, the situation comes into play here where you don't want to create a path that the current can go on and alter the circuit that you have. And so when you have a voltmeter, you actually want to have a really, really, really high resistance because you don't want to create a path for that current to travel and then divert it from the path that it's already going on. And so in order for a voltmeter to measure the voltage but not impact the rest of the circuit, the voltmeter needs to be connected in parallel with the component that you're taking the voltage of. And then it also needs to have an infinite resistance. Now, reality is infinite isn't a number, it's just an idea. And so they usually make voltmeters with just a really, 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 really high resistance. And so in here it says 10 mega ohms. So something that's not going to impact most things and will block the current from going through it except a teeny tiny trickle that'll be enough to figure out what the voltage is across that component. So lastly, if we look at this schematic of an ammeter and a voltmeter that's being used in the circuit, you can see that the ammeter is in series with the rest of the circuit. That allows the current to pass through it, and the resistance on that ammeter is incredibly low, so it doesn't affect the way that the current behaves within the circuit. And then the voltmeter is connected in parallel. It's taking the voltage drop across component X there, and the voltmeter has a really high resistance, so current isn't splitting to go along there, just a tiny, tiny, tiny amount ends up doing that, and it doesn't alter the current that's going through the component X there.